In this video, we're going to look at completing part 2 of our Calculus Notes booklet. Jumping into it, Introduction to Differentiation. Differentiation is the process of taking the derivative of a function. Recall, when you first used first principles, you find a function that when you substitute in a specific point, you are given the value of the slope of the tangent to that point. So recall, when you use first principles, you find a function. You find a function that when you substitute in the specific point, you are given the value of the slope of the tangent to the point. Going down. An alternative notion or notation for the derivative is the following. In general, if y is a function of x, then the derivative of y with respect to x is denoted as dy over dx. So this in itself is the same as writing f of x, but this is Leibniz's notation. Similarly, if z is a function of t, then the derivative of z with respect to t is denoted as dz over dt. Now, up until this point here, when we've been calculating the instantaneous slope or the tangent to a particular function, we've been using first principles. However, you may have noticed that there's a pattern to what's happening when we do the derivative. So notice that if you found f of x, so the slope of f of x, where f of x is defined as x, you'd find using first principles that the function describing the slope is simply defined as 1. Similarly, for a function f of x defined as x squared, you'd find that the slope of the function f dash of x is defined as 2x. And similarly, for a function that's definition is x cubed, the derivative is 3x squared. So notice that for all of these, we get the power and we multiply, or we bring the power down in front like so. And then we take 1 from the power like that. So this used to be 3, but now it's 2, so it's 3 minus 1. So what we're seeing here is something called the simple power rule. The way in which we can write that is, this suggests the following result. It is known as a simple power rule for f of x, where f of x is defined as x to the power of n. We can say that by this rule we've just observed, we can say that f dash of x can be easily derived as nx to the n minus 1, like so. So that's n times x. So what this is called is the simple power rule. It's a pattern that allows us to differentiate functions on the fly. So going down, going up slightly, applications of the simple power rule for constant function. So if f of x is defined as c, then f dash of x is simply 0. So remember, with this function here, if we graph this, it would simply be a straight line, so the slope itself would be 0. Now for a linear function where f of x is defined as mx plus c, think about what is the slope of this function, and it's m. Now, if we use our rule or simple power rule, we would note that f dash of x would become m and then x 1 minus 1, and that would in turn become 0. And because it becomes 0, then the definition of this function is simply m. So that's pretty consistent with what we've already been seeing. Now going down, constant product rule. If f of x is defined as k of g of x, where k is a constant, then what we'll find is that the function f of x is going to be k g dash of x. So recall that, or think about it. If f of x is a function dependent on x itself, and k is a constant, so this one here is constant, and g of x is a function similar to f of x. So the only difference with f of x and g of x is that f of x has a dilation of k. So the derivative of this function f of x is simply k times the derivative of g of x. And finally, going over, if we've got a function f of x where its definition is g of x plus h of x, then f of x will be defined as g dash of x plus h dash of x, like so. And of course the difference is simply the same as the sum, but with the opposite sign. Like so. Perfect. Alright, moving onwards. Let's get into a few examples. So it's asking differentiate each of the following. So using this new rule that we've come up with, say for example, if we've got f of x equals x cubed, then our f of x is this. And let's think about, we want to get f dash of x, so the function that's going to explain the slope of this original function f of x. Using the simple power rule, I'm going to grab the 3, and we'll bring the 3 down the front. The x will stay there, then our 3 will be up there, but we're going to take 1 from there. So what this will leave us with is 3x squared. So the derivative of f of x, or f dash of x, is simply 3x squared. If we use first principles, we'd end up with this result as well. So what we've managed to do is achieve what first principles would tell us, but in a matter of one line. Going across to b, we've got f of x equals 5x squared. Now f dash of x, using our simple power rule, we're going to have the power, the 2 up here, it's going to come down, multiply with the 5, like so. The x will stay there, then it will be x squared, take 1. Evaluating, so these two coefficients, it's going to become 10x to the 1. And we know using our index laws, we don't need a 1 there because the 1 is implied. So we can go 10x. So the derivative of f of x, or the derivative of 5 times x squared, is simply 10x. Alright, going down to something a little bit more challenging. Let's say f of x is defined as 4x cubed plus 6x squared plus 12x plus 1. Alright, using our simple power rule and the sum of all of these terms, we can say that f of, or f dash of x, will be, say, 3 times 4x 3, take 1, then 2 times 6x to the power of 2, and then take it down a notch, plus, we'll go 1 times 12x 1, take 1, and then we've got this floating constant here. This constant, because it doesn't have an x in there, it simply becomes plus 0. So the 1 gets cut off. Awesome. Now, evaluating these expressions, or these terms we have, we've got 3 4s are 12x, 3 minus 1 is 2, plus 12x 1, so I just leave it as an implied 1, plus 12x 1 take 1, which is 0. And evaluating that, we get f dash of x is equal to 12x squared plus 12x plus 12. So this is our definition here of the function f dash of x, which explains the curve or the slope of f of x. So notice how we've gone down 1 order of magnitude. Up in this one, we're in magnitude or order 3, where in contrast for this one, we're of order 2. Alright, going on to something a little bit more tricky. We've got f of x equals 3x cubed plus 2x minus 3 over x plus 5 over x cubed. Now we might immediately be distressed when we see these x's on the bottom, but let's just keep in mind that we know our index laws, and our index laws will allow us to make easy work of this. So I'm going to rewrite this out as f of x equals 3x cubed plus 2x minus 3, and then I'm going to grab the x down here, bring it up here, and then say it's to the power of negative 1. Similarly for the 5, I'm going to grab the x and say it's not 3 but negative 3. Okay, now that we've got this sorted, we're ready to differentiate it using our simple power rule. 3 times 3x 3 take 1 plus 2x 1 take 1, and if we want to be pedantic we can put the 1 out front there, minus negative 1 times 3x minus 1, and you guessed it, take 1, plus minus 3 times 5x minus 3, take 1. Evaluating this expression on the right, we've got 9x to the squared plus 2x to the 0, and then minus negative, so this is going to be minus negative 3x to the negative 2 plus minus 15x to the negative 4. Cleaning all of this up, we're going to get x, or 9x squared, plus 2x to the 0. The x to the 0 becomes 0, or 1, I should say, so it's just 2. The double negative becomes a positive 3x to the negative 2, and the plus goes away because it's plus minus 15x to the negative 4, like so. And we could leave that as our definition for f dash of x, or if we want to write it in a similar form to what we saw up here, then we can write it as f dash of x equals 9x squared plus 2 plus, then downstairs it's an x squared and upstairs it's a coefficient of 3, take 15 over x to the negative 4, like so. And thus we are done. Alright, in the next example of E, we are challenged with an equation that contains our favorite things in the world, which are surds. So the definition of this function is y equals 3x squared minus 5 root x. Now, working with surds, we have the notation here of the radical symbol. Now remember, the radical symbol might look fancy, but it's not actually helpful when we're trying to math this sort of thing. So as always, whenever we see a radical and we know we have to do some form of mathematics with it, what we're going to do is we're going to rewrite it in its index form. So I'll rewrite the expression on the right as 3x squared minus 5. Then in parentheses, it will be x to the power of a half. Now, you might have figured out what's going to go on here. Well, I'll change it ever so slightly, and I won't put it in parentheses. We'll get rid of those, and we'll just have it as x to the power of a half. Perfect. All right, now I'm going to go in for the derivative. So I'm going to use Leibniz's notation, go dy over dx, like so. And using the simple power rule, we're going to get 2 times 3x squared minus 1. And then it will be minus, and the power itself here is a half. So we're going to get a half times 5x, power of a half, take 1. Interesting. Going down, evaluating the coefficients, 2 times 3 is 6x to the 1 minus, it's going to be 5 on 2, like so. Then x to the half take 1, so that's going to become negative a half. Interesting. All right, moving down, we've got 6x to the 1, which is simply 6x take, and then we've got this 5 over 2, and we've got the x to the negative a half. Now, this one isn't that great, writing it like that. So because I've got the 2 on the bottom, what I'm going to do is I'm just going to rewrite the x on the bottom to get rid of the negative power, like so. And then I'm going to change it ever so slightly because we're done. Our definition of the derivatives is dy over dx. So I'm going to put it in a prettier form. And I won't write it as x to the half, but rather the way in which I'll write it is downstairs we'll have 2 root x over 5. Yes, 2. Alright, so what we're going to do is, this one's a little bit tricky. The first thing we need to do is we need to put it in a form that's easy to work with. So what I can instantly see that's standing between us and success is firstly this perfect square up top, and then secondly we've got this cube root down the bottom. What I'm going to do is I'm going to crack all of these open and then simplify it with index laws. So we're going to get y equals, and we'll say that's going to be 9x squared minus 12x, I believe. And then we're going to have plus 4. And all of this is divided by x to the third. Going onwards, we're going to have 9x squared times x to the negative third. Because this one is now in the numerator, it becomes a negative third. And we're splitting all of these terms up. Then 12x times x to the negative third, and then plus 4x to the negative third. Now we have to collect like terms, or we have to simplify these terms out. So the way in which we're going to do that is it will be 9, then it will be 2 take 1 over 3 minus 12, and that will be x, 1 take 1 over 3 plus 4x to the negative third. Cleaning it all up, we're going to get 9x, and this will be, the 2 will become 6 over 3, so we'll get 5 over 3, like that, minus 12, and that will become 2/3, and then finally 4 and minus 1/3. So it looks a little bit messy, but again, nothing we really can't handle, just some index laws. Alright, so now taking the derivative, we're going to get dy over dx, or change in y with respect to change in x. Then we simply get the power, 5 over 3, multiply it by our original coefficient, then the power 5 over 3, and we're going to take it down a notch, minus 2 over 3 times 12x 2 over 3, take 1 off, as that is our rule, plus 4, and I'm a little bit ahead of myself, not plus 4, but times negative 1 over 3 times 4x, negative 1 over 3, and then take 1. Evaluating all of this out, we're going to get 5 over 3 times 9. Well, we can deal with the 9 divided by 3 is 3, so it will be 15x, and then 2/3. Take 2 over 3 times 12, or the 12 divided by 3 is 4, so that will become 8x, and then minus 1/3, I believe. And then we've got a minus 1 over, so that will be 4 over 3x, and then that will become minus 4 over 3 here as well. Awesome. So what we've got is a definition of our derivative, dy over dx. And if we wanted to simplify it a little bit more, we could go a bit further and put it back in its form it was originally in, and in which case we would get, say for example, or if we express it as the radicals, we're going to get 15, and then it will be the cube root of x squared minus the 8 on top, then it will be the cube root of x minus 4 over 3, so that will be 3 some sort of cubic root of x to the power of 4, where the 4 is on top here. Question 2. Find the slope of the tangent to the curve y equals 3x squared plus 7 plus 2 over x at the point where x equals 2. So all this is asking is differentiate the function y here, and then substitute the value of x into the derivative of y to tell us the slope of y at the value of x given here. So first things first, we're going to find the derivative of the function y. Writing y out, we're going to get 3x squared plus 7 plus 2 over x. Notice with this one, it's nothing particularly challenging about the terms 3x squared and 7, but 2 over x, that's a little bit tricky, so we're going to rewrite it using our index notation. So it becomes 3x squared plus 7 plus 2x to the negative 1. Now finding the derivative, dy over dx, we're going to get that will become 6x to the 1 plus 0, and then we're going to get minus 2x to the negative 2. And then simplifying that out, it will become 6x minus 2x to the negative 2. Alright, cool. Now we want to find the value of the slope, or the gradient of the function y, where x equals 2. So simply all we're going to do is we're going to use the notation dy over dx, then the little dash here, for x equals 2. And then wherever we see x, we simply substitute in 2. Alright, too easy. Evaluating this, we're going to get 12 minus 2 over 2 squared. And then that will become 12 minus 2 over 4, which becomes 12 minus 0.5, which is 11.5.